a series of joint UNC-Duke colloquia, physics colloquia. I guess I should say physics and astronomy colloquia. um, uh, I'm Joshua Sokolar, and I just want to remind you to please keep your computer muted unless you're speaking. If you would like to ask a question during the meeting, please use the raise hand feature or send me a chat message, and I will try to break in at an appropriate moment. Please just use that for questions of clarification, simple things. If you have a longer issue to discuss, we'll have plenty of time for that when the talk is over. I also wanted to just put a plug in for the last colloquium that we'll have this semester, which will be on December 2nd. It will be Carl Williams from the National Institute of Standards and Technology talking about quantum information and quantum computing from the national lab's perspective. Something about the current state of the art and something about the strategy for supporting that kind of research and what might be expected in the coming years. So I strongly encourage people to show up December 2nd, so the week after Thanksgiving for that. And now I'm going to turn it over to Joaquin Droot to introduce our speaker.
Thanks, Josh. It's a pleasure to introduce our very own Nick Law today. Nick got his PhD in astronomy at the University of Cambridge in the UK in 2006. Then he was a postdoctoral scholar in astronomy at Caltech until 2009. And after that, he was also a postdoc at the Dunlop Institute at the University of Toronto until 2013, when he came to UNC, first as a visiting assistant professor, then assistant professor, and now, as of last year, associate professor. He's received multiple honors. I'll just mention two: the NSF Career Award and a SciLog. He's also a SciLog fellow, and you can see already from this first slide the multiple grants, which are certainly a kind of honor. I gotta say, I'm a huge fan of building things and using them to do science. So I'm very much looking forward to this talk. And in a way, what a better way to take our minds off of the election a little bit and spend some time listening to some great science. So without further ado, Nick, please take it away.
Yes, thank you very much, and thank you everyone for coming. And hopefully, as Joaquin says, I can distract you from your doom scrolling for at least a little while. And yes, I promise I won't have this many badges and sponsorship deals and that kind of thing on the rest of my slides. I felt it was best to get them out of the way. So I'm going to be talking about the telescope you can see behind all of the junk on the front of this slide. And this telescope is designed to work in really a different way from almost every other telescope. So it's designed to look at the dynamic sky, look at doing what we call time domain astronomy, that is looking for things changing in the sky. And it's a big sky. And so almost every survey, the way they address this is with a large telescope, which looks at a relatively small part of the sky, maybe the size of the full moon or a bit bigger than the full moon. And then when you have a telescope like that, the way this works is you look at one part of the sky and build up some coverage over individual small chunks of the sky. And then over multiple nights or multiple weeks or multiple months or multiple years, you start building up more and more sky coverage, and you can start to see how things change in the sky. What this does is it sets a fundamental limit in how rapidly you can understand what's changing. You can do deep drilling on very small fields, go really fast and look at a very small field continuously, or you can take usually on the order of several nights to several weeks to cover the entire sky and come back and start again and look for things that have changed. You can do some combination thereof. If you want to cover wider fields, larger areas of the sky, what's generally done is to put together multiple telescopes. So you have, so there are lots of these telescope arrays existing in astronomy that put together individual telescopes just to get wider coverage. The system that we have built is kind of the logical endpoint of that type of design, where we're covering the entire sky in every exposure. So that's what you're seeing here. This is an array of individual cameras, and each of those cameras covers a relatively small part of the sky, but together they cover the entire sky. So this is the system is roughly a gigapixel, 700 megapixels, covering an 8,000 square degree field of view. So you can think of that as the same field of view as your eyes, but able to detect objects 10,000 times fainter and with about an order of magnitude better angular resolution. And what this allows us to do is simultaneous long-term and high cadence monitoring of millions of targets across the sky simultaneously, rather than targeting individual regions or waiting weeks for things to go past. Now, I will admit this is a weird looking telescope. Popular Mechanics called it bug-eyed. Science magazine said it looked more like an architectural folly than a telescope. And my favorite one actually was Science News, like an upside down colander repurposed into a Star Trek prop, which is a very apt description of it, I think. But there is actually a lot of engineering going on behind why we're doing it this way. When you build a robotic telescope system, you really have to make sure that you've got a reliable system, and reliability means a small number of moving parts. By building this hemispherical dome, or as we call it, the mushroom, we can pot each of our cameras into the common dome, and then all we have to do is rotate that dome with the sky to keep all of the cameras tracking their individual parts of the sky simultaneously with only one moving part. And that really improves the reliability of the system. So the whole thing is about 6 feet across and made of fiberglass on the outside. I'm not going to go into the engineering much of the system here. I'm going to talk more about the science results we've received from it and some of the software side of things. But suffice to say, it's a fairly complicated system to get working. What this means, what this type of survey means is we're doing something quite new here. We've got small telescopes. These are telescopes that are literally camera lenses you can buy in Best Buy. But each of those telescopes gets to observe their part of the sky for 6 to 8 hours each night. It's not like they're flitting between different fields. And that means over time, we build up deep images of the sky. As we put together those thousands of individual frames, we can actually go to quite faint objects and detect new objects that are a lot fainter than we could see on individual exposures. We have 2 of these systems. The Evryscope South has been running at CTIO in Chile since the end of 2015, and the Evryscope North has been running for about a year and a half at the Mount Laguna Observatory in California. And what these 2 systems do, of course, is allow us to cover the north and the south, northern and southern skies, and build up quite large data sets across the entire sky. This is what one Evryscope image looks like. It's 100 degrees across, 36,000 pixels across. We get a 2 gigabyte image from each of the Evryscopes every 2 minutes. So it's a fair amount of data that's produced, on the order of 360 gigabytes a night. We've collected roughly half a petabyte of data from the systems so far, and that's rapidly increasing. So if we zoom in on one small section of this image, this is now 1% of that previous image. You see, well, it's full of stars, and this is what we're monitoring. We're monitoring all of these stars for anything changing, whether that's planets going in front of them or other objects. For example, if I zoom further into this image, if I take 1% of that 1% of the image, this is a comet moving through that image. This view is 0.03% of the Evryscope field of view, and of course we get everything else in the sky simultaneously with this. So what that means is we've built up, we get up hundreds of data points, hundreds of light measurements on 8 million stars per night. at a total of 2 trillion photometric measurements of the brightnesses of individual stars so far. And of course, we're not just looking at the stars. Most of what I'm going to be talking about today is actually what goes on between the stars in the blank parts of the sky that don't have anything noticeable in them. And we're looking for events in there. 40 terabytes of photometric data. And we have, as I said, actually I have 1 petabyte, north and south, about 1 petabyte of imaging data uncompressed from the systems. That 40 terabytes of photometric data is just the size of our database, just the database of star brightness measurements after everything has been processed. So the systems have been running for a while. There's lots of people around the world using data from the systems. This slide's a little bit out of date, I notice now, so it's a lot more than 15 institutions now, and lots of people are using them. I should mention there are a lot of different science results from the Evryscope. I'm not going to talk about most of them. I really weighed it up whether I should try to do an overview of everything the Evryscopes do. But I thought that would rapidly get kind of overwhelming and not allow me to go into interesting detail on individual things. So I've selected a few particular science areas in terms of rapid events that happen on the sky, in the sky, that I'm going to talk about. So I'm not going to talk about the surveys that my students and collaborators have done looking at activity and variability of young stars, looking for gamma ray burst objects across the sky, looking at hot subdwarf stars, discovering whole new classes of hot subdwarf stars. We've seen white dwarfs crystallizing as they cool from being undegenerate to degenerate objects. And there's a whole class of other things to talk about. These are the Evryscope publications so far. This number is rapidly increasing. We've had about, I think, 8 publications so far this year. Lots more in the pipeline. So I'm not going to go into the details of those. I'm just going to select individual things that I think form a coherent story. And I want to acknowledge, of course, that this is the work of actually, by astronomical standards, quite a small team, mostly students at UNC. I'm going to highlight some of their individual research projects. And really, I'm talking about their work. They built the systems. You can see here, Nathan, for example, maintaining one of the Evryscopes, other students and postdocs building the systems. It's really their work that I'm discussing here. So any of them who are signed in, I think several are. Thanks very much, guys. You've been doing great. So let me start with mysterious flashes. So the kind of storyline I'm going to follow with the talk is, what do we see on a typical night? When we turn these systems on, we take the 1.7 gigapixels of images every 2 minutes between the two systems. What do we actually see? And what do we see that's most interesting? So I'm going to start with one of the things that somewhat confused us from when we first turned on the systems that were capable of finding transient events, new events in the sky. And I'd just like to mention that this is the result. This is a result that one of my students has got accepted in AppJ letters. It's actually going to be released tomorrow. We're putting out a press release tomorrow. So I put a little no tweet symbol on the slide. Please keep this close to your chests until tomorrow, when we're going to release it. So this is what these mysterious flashes look like. Blank part of the sky, and then a new thing. And then usually that thing goes away again. We see them in individual images, and then they vanish. And we see these all across the sky. We see lots of these. Here is another couple of examples of a more crowded field, where what we're actually showing here is our image subtraction system. When we find new events with the Evryscope, one of the things we want to do is make sure we're not being fooled by pre-existing stars. If we turned the systems on and said, wow, we found 15 million stars every 2 minutes, it obviously wouldn't be very helpful. So what we do is we take images And then we take images later and we subtract the initial images from the ones that we've taken later to find new events that have changed. And as you can see, what happens there is on the left-hand side of the plots is the previous images we took. The middle ones are the new images, and anything that's new gets saved into our difference images. Anything that's not new gets removed. And that's how we discover new events in the sky. The way we actually do this is with a fairly complicated system called the Evryscope Fast Transient Explorer. This was the subject of the PhD thesis of Hank Corbett, who's one of my students who's close to graduating. He's worked a long time on this and it works really well. And I wish I had more time to go into how it works, but we're going to talk about the results from it mostly. But suffice to say, it's a multiple layered system, all from subtracting off the images using algorithms to make sure those images are well aligned and have the same shapes of stars and that kind of thing, all the way through to a machine learning neural network based system which knows what is a subtraction artifact and what is a real actual astrophysical event. And we've taught it how to do that. So we're not looking at the hundreds of thousands of things we see each night. The computers are looking at that and picking out the most interesting things for us to look at. Crucially and quite uniquely, this is an extremely real-time system. We get that 2 gigapixel image every 2 minutes from each system, 700 megapixel from each system, 2 gigapixels across the sky. And the system that Hank has put together is able to process those images within a minute of being taken, which means we have the capacity of not only seeing things in the sky, but rapidly following them up, rapidly seeing what they are. And I'll talk later about the surveys we're doing with that capability. But back to those flashes. FD, our fast transient detection system, has seen these flashes all across the sky in large rates. So what you're seeing on these graphs is the left-hand side is cumulative number of flashes as a function of magnitude, which is thus the brightness of the stars. Towards the right is fainter detections. And on the right is the non-cumulative, just the kind of binned version of that plot. The 4 panels, the ones in yellow, show the south celestial pole, the region around the south celestial pole. The purple shows the equator, region around the equator. And so there are a few takeaway things from this plot. These mysterious flashes, which come and go in individual images, occur at massive rates, 1,000 times an hour across at the south celestial pole, 4,000 times an hour near the equator. These are very, very common events that are present in almost every astronomical survey. And when you talk with astronomers, they say, oh yeah, we've seen these. We've always wondered what they are. They go away after a single image and they never come back. And what most surveys do is actually, they're not capable of seeing these events because they throw out anything that they only see on an individual image, because this type of thing is such a large problem, along with moving objects like asteroids and so on. The other takeaway from these plots is that there are a lot more of them at the equator than there are at the south celestial pole. And this immediately implies these are something to do with the Earth. It's not clear why you would have anything cosmological that would be aligned with our Earth's axis, although it could still be something in the solar system. But if we look in more detail at those flash rates across the sky, what we see is they're actually correlated with the Earth's shadow. So this is a plot, you can think of this as looking down from the top of the Earth with sunlight coming from the left, and the coloration on the plot corresponds to how many of the flashes we see. Now, we don't know, sorry, the radius on the plot, the distance from the Earth, corresponds to literally the physical distance from the Earth. We don't know that distance for these flashes, we just see them as flashes, but we've plotted the distance on here because when you look at the coloration, numbers of flashes we see at different locations around the Earth, you can see there are very obvious trends that 90 degrees to the sunlight has a lot more flashes than directly away from the sunlight. And there is a disallowed region for where these flashes occur, which is in the shadow of the Earth's orbit. There's in the area that is, if the flashes were coming from low Earth orbit, that means that a larger angular radius is in the Earth's shadow, and we see a large jump down in the flash distribution due to that. At geostationary orbit, the edge of this plot, essentially the number of flashes goes to 0 in the region of geostationary orbit that is shadowed by the Earth. So what we're seeing here is things in Earth orbit. And actually we can see this for some of the flashes. So minute to minute to minute, this is a flash that we tracked across 20 degrees or so of the sky. And what you're seeing here is that individual flash occurring every few minutes in different Evryscope images. And we've been able to track some of these objects over quite long distances across the sky. So what's going on here is these are Earth orbiting things. And this is, things like this may be familiar to some of you in that satellite flares are seen. These are very bright things, easily naked eye visible. And they occur, you see a moving object which flares up over the course of a few seconds and then flares back down. And what's going on there is that there's a satellite with a flat reflective surface that is catching the light. The objects we're seeing cannot be satellites because the flash rate, the time of that flare is so much faster than anything seen before. This is the typical kind of rate for one of those flares that have been seen before. They last seconds. The events we're seeing have to last milliseconds, and we know that because as we track them across the sky, they look like stars. They don't look like moving objects. We see satellite streaks all over our images. They don't look like that. They look like individual stars. And the problem with that is if they look like individual stars, they can form foregrounds. They really are things that you would think could actually be a real astrophysical detection of something beyond Earth orbit. So as an example for where that can be a problem, fast radio bursts have been in the news a lot recently. These are mysterious events which we know come from outside our galaxy. They're seen by systems like this is the CHIME Radio Observatory, and they are millisecond timescale events. So along the x-axis of this graph is time in milliseconds, and the y-axis is on the bottom panel frequency, on the top panel just intensity. These are millisecond timescale radio flashes. And the question is, are there any optical flashes associated with them? Some of these fast radio bursts repeat. Some of them have been traced to individual galaxies that they come from. But if we can find optical light coming from those flashes, that really constrains what the central engine of them might be. But that's really, really hard because they last milliseconds. So you can't slew a telescope. You can't have a radio observatory say, we saw one of these things and then get an optical observatory there soon. What you have to do is observe the entire sky looking for these flashes. But there's this huge foreground. So across the sky, there are an average of 2,000 of these flashes per hour. And if you think of those rates, that means if you're looking into the sky for a minute, you're more likely than not to see one of them with your naked eyes. And that sounds weird because we're looking at these with a telescope. But what's actually going on is your eyes have a very short integration time compared to a standard telescope. Your eyes have an integration time of a second or less. And so a flash that lasts a millisecond appears much brighter to your eyes than it does to a telescope where that millisecond of light is diluted over minutes of exposure. And so many of these flashes are actually naked eye. In fact, many of them are not faint naked eye. They are visible from Chapel Hill naked eye if you wait long enough. And if you've ever caught a little glimmer out of the corner of your eye looking up in the sky and it's gone before you've even realized it's there, that might not be your eyes just playing a trick on you. It might actually be a real flash from these objects in Earth orbit. And the actual rates of these flashes is many orders of magnitude higher than the rates of public alerts from essentially all of astronomy. So if you see a rapid flash in astronomy, you're much more likely, and this is what we've found with the Evryscope, no one had numbers on this before. Our numbers show that you're far more likely to see these flashes than you are to see a real astrophysical object if you see a very rapidly changing thing. And so these are a dominating foreground for fast transients, and they have to be dealt with. One way you can deal with them is with localizations. If you know in the sky roughly where these things occur, where the object you're interested in is, then you've got a chance of, then the probability of a flash being associated with that object goes down. But if you have something where the localization is not clear, like a gamma ray, like a gravitational wave event I'm going to talk about later in the talk, then that's a real problem, and you have to figure out some other way of dealing with these flashes. You could have multiple telescopes looking at these things from different places, or you can track the orbital motion of these satellites. My student Alan Vasquez is looking at how to do that, to track the orbital motion so we can remove these events. But once you have removed them, you have the opportunity to go and do astrophysics, and this is what we've been spending a lot of time doing. And I'm talking here primarily about the work of my student Ward Howard. Ward has been looking at the astrophysical transients that we see with Evryscope, and in particular, flares. So this is an example of a flare from the sun. As you can see, these can be quite spectacular events, and we see these very routinely in Evryscope data. This is an example from FD of a M-dwarf superflare going off. So this is tracking a typical cool star. An M-dwarf is a cool small star, much smaller than the sun, from about half the sun's mass and radius down to about 1/10 of the sun's mass and radius, spanning that range. This is a star that got very much brighter for a period of time. And this is a particular concern for exoplanets, because you could imagine, in this case, the star got roughly 50 times brighter for a few minutes. And you could imagine what would happen to our sun if it got 50 times brighter for a few minutes. Well, actually, I misspoke. The sun would be fine. The Earth would not be. The Earth would be having an interesting time if the sun got 50 times brighter. And so there's a huge amount of research being done at the moment on the impact of flares on planet habitability. Can planets even survive the flare rates of some of the stars that we see? These small, cool stars make up most of the stars in our galaxy, and they're stable for far longer than a star like our sun. Our sun is actually a hot burning, fast, short-lived, kind of extreme star compared to most of the stars in the galaxy. Most of the stars are the cool M-dwarfs that last burn for even trillions of years, and may offer very stable locations for life to survive. But they produce these flares in prodigious numbers. And the question is, what effect do those flares have on the surface of those planets? It's easy to blithely say, you know, the sun gets 50 times brighter and that sounds bad. But what does it actually do to these planets? So that's what we've been looking at. The first example that we've been looking at is this star here. So this is 0.006% of the Evryscope field of view. And on St. Patrick's Day 2016, I believe, this happened to that particular star. So that got about 100 times, I'll run that again. The star got about 100 times brighter over the course of a few minutes and stayed quite bright for the next half hour or so. This isn't just any star though. This is Proxima Centauri. This is the star. This is a graph of the star's of Proxima Centauri's brightness over time. Proxima Centauri is our closest stellar neighbor, and it's incredibly active. It's actually suspiciously active. It should be an old, slowly rotating M-dwarf, but it's active as if it was a young star, which is an interesting thing that if someone wants to ask me a question about, we can get into. But it is incredibly active, and it's also thought to host the nearest habitable planet to us. It's an amazing thing that the closest star to us, apart from the sun, seems to host a planet in the habitable zone. But it's a real thing. It's been confirmed, and that means that we're really interested when Proxima gets so much bigger and brighter for so long, about what that could do to that planet. And in fact, with Evryscope monitoring, we've been able to show that Proxima does this a lot. So this is a graph of time of Evryscope monitoring and the brightness of the flares that we see from the star. The superflare on the left is the big bright spike. This is a logarithmic scale, and so you can see there are lots of smaller flares, although the superflare was quite an exceptional event. So there's a lot of activity from Proxima Centauri. What that activity actually does is it destroys the ozone layer of any kind of putative Earth-like planet around Proxima B. So Ward collaborated with atmospheric chemists to figure out what these flares actually do to an Earth-like atmosphere. What happens is the flares, or actually, if you want to get into the details, the protons associated with the flares and coronal mass ejections dissociate nitrogen in the atmosphere, and that dissociated nitrogen can go and destroy the ozone layer of the planets. And essentially, given the flare rates we're seeing from Proxima, you lose most of your ozone over the course of a few years. And then the thing is, the flares keep on nailing the planet, and every time the ozone starts to recover, it gets smushed back down again by the flares. Now, obviously, we've had our own problems with the ozone layer on the Earth, and not everyone in Australia died because of the ozone layer hole, although they had to wear sunscreen a lot. So the question is, what implications does this have for habitability? Well, the problem is these flares are destroying the ozone layer, and then the flares come in and give a double punch of massive ultraviolet light. So these flares are essentially very hot black bodies with some emission lines superimposed, but those hot black bodies produce massive amounts of ultraviolet light compared to these cool stars. These cool stars have surface temperatures of 3000 Kelvin, thousands of Kelvin. These flares have temperatures of at least 9,000, maybe more Kelvin. And so they have massive ultraviolet light. And so this graph this converts the ultraviolet light on the received by the surface of a planet unprotected because its ozone layer has been destroyed into, it's converting the units into ones that are important medically. And the reason for that is, well, let me give you an example of an Earth organism. This is Diococcus radiodurans. This is the organism that is the most radiation tolerant microorganism on Earth. It's found in the high Chilean deserts where there is little UV protection. It's found even, it's even capable of surviving radioisotope radiation in nuclear reactors and things. It's got incredible DNA repair capabilities. At the surface of Proxima B, given the ozone layer has been destroyed, the ultraviolet just from the one Proxima superflare, this massive flare, is enough to kill this, to kill the most radiation tolerant microorganism on the Earth 100 times over. So that is quite a bummer for life. I mean, it's difficult to understand how surface life could exist on Proxima B if it's dealt with those kind of flares happening all the time. Now, that doesn't stop protected life evolving. Life in the oceans would be okay, assuming your oceans can survive the repeated impacts of those flares. Something that the field is looking at the moment is, as these flares impact Proxima, is just the atmosphere itself stripped away by the impact of these flares and coronal mass ejections. If that doesn't happen, these flares are bright enough that surface life is going to have to really adapt very strongly to survive these flares, maybe by running and hiding or something like that, running and hiding under rock. So I'll talk more about the biological effects of these flares in a little while, but I want to talk a little bit about what we can do with these long-term observations that we have of flares. TESS is a survey that is covering the entire sky. It's a space-based survey run by NASA looking for planets. And it's capable of looking at the entire sky for tens of days. And so we have a lot of surveys that are running simultaneously between TESS and Evryscope, taking advantage of the fact that both surveys are observing simultaneously. I'll talk about those in a minute. But one of the real differences between TESS and Evryscope data is Evryscope observes these targets for much longer. Rather than tens of days, it observes them for years. And so we can look for rare events, these massive superflares, the ones that can really affect the atmospheres of these planets. So my student Amy Glazier has been looking at this for one particular system called the Trappist1 System. This is an amazing exoplanet system which has 7 planets, 3 of which are in the habitable zone for this very cool star. And the question is, okay, these planets are in the habitable zone, which means that they are rocks with the right temperature for liquid water. Of course, our moon is a rock with the right temperature for liquid water and isn't especially habitable. So we want to get into the details of how habitable these planets might actually be. So what Amy has been looking at is developing what we call the flare frequency diagram for these, or distribution for these events, trying to figure out how often these major flares occur. Now, it turns out TRAPPIST-1 is actually too faint for us to see in Evryscope, but that's okay. We would see the major flares coming from the system. If there are flares that are big enough to affect life, we would see them in the individual Evryscope images. And this is important not only to see if the planet could survive, but actually, believe it or not, about whether life could evolve on the surface of this planet at all. So if we think about abiogenesis, which is a fancy word for how you make life, from inorganic compounds, from just chemicals lying around in warm pools, warm geothermal pools, or however you would like to do it. It turns out if you assume life starts with RNA, as we have one example, and what that one example, it seems it did. If you assume life starts from RNA, you need to make RNA. And you can't have life make that RNA, you need to make the RNA via some kind of inorganic synthesis route. And it turns out, chemists and biophysicists, biochemists have been looking into this in an inordinate amount of detail. It turns out the pathways, the only pathways we know of to make RNA from anything that would be lying around on the surface of a planet is using ultraviolet light. So there's a reaction chain I'm showing on this slide here, where you start out with base components and you apply ultraviolet light to those base components, and they form more complicated components. The ultraviolet light is required for that reaction to happen. In blue is where the ultraviolet light occurs. The blue in the center of the slide is interesting because this is a rate limiting step. This is not something that can take place slowly. You can't wait for individual flares. You can't form some stuff, wait for months, and then wait for the next flare to make more complicated compounds, because in the dark, your compounds rapidly decay into what is essentially brown goop. That's the path that says H2S, hydrogen sulfide in the dark. You rapidly form brown goop that ain't no life. To make RNA, you need a particular amount of ultraviolet light to prevent that brown goop occurring. And that actually sets a limit on whether you can form life on the surface of a planet according to the biochemical pathways we're aware of at the moment. And so what Amy was able to do is take this flare frequency diagram and draw 2 regions on the plot. So along the x-axis here is the brightness of the flare events, and on the y-axis is the number of flares. Brighter events towards the right, more flares towards the left. So faint flares are much more common than large flares. To avoid, so I should say the red line is our best guess for a power law model underlying that flare frequency distribution. Whether it should be a flat power law through the entire fit is definitely up for debate, but let's use this one for now. If you do more complicated things, it actually gets worse than the results I'm going to mention. The 2 regions you see here, the yellow region is the ozone depletion zone. This is where the flares are bright and often enough that you lose the ozone on your planet, and then your planet gets irradiated by ultraviolet light, and then you may well lose the atmosphere entirely, and it's not very habitable. Unlike Proxima Centauri B, there are not nearly enough flares to get into the ozone depletion zone. These planets are safe in the same way that we are safe from the relatively small flares produced by our sun. However, as far as we can tell, the flares are orders of magnitude away from also being in the abiogenesis zone and producing enough ultraviolet light that life could form on these planets. So at least Earth-like life seems difficult to form on these planets, knowing what we know about the ultraviolet radiation involved. Okay, so I've shown you 2 targets now, but I've been saying, of course, we're looking at millions upon millions of targets with the Evryscope. So let's talk about more. We want to know really what are the best home places to look for life in terms of habitability, and even what are the best places to, if we know there are habitable worlds, to actually target telescopes to and see if those habitable worlds still have atmospheres, still have the capability of generating life. And so we've been doing this in conjunction and collaboration and frankly funding with TESS, where we have been looking at stars, cool stars across the sky, looking to see the effects of these flares. We've seen hundreds of these flares. We've found hundreds of superflares, which are flares which are vastly larger than those which the sun produces. We've found 8 flares where the star gets between 10 and 250 times brighter. These are the ones, these are world devastating flares. In fact, we saw one flare bright enough that could actually destroy the ozone layer totally of a planet in a single event, and probably knock a bit of the planet's atmosphere out from the planet as well. And in a single event, repeat that over billions of years, every few months, and that planet is frankly screwed. So we've seen lots and lots of these flares. Ward has seen lots and lots of these flares. It's kind of fun. These results have kind of caught the interest of a lot of people in the community. So there's an international team that's actually starting to simulate the effects of our flares on life. So they're actually simulating these ultraviolet events on things like the extremely hardy microorganisms that we're wondering if they would survive. And what they find is quite surprising. They find that almost all these microorganisms are killed instantaneously. And that's what we wrote our papers on the basis of, that you look at the lethal dose and you for the microorganisms, and where these flares are vastly beyond the lethal dose. However, what this team found is that a few of them hardily cling on to life following the flare. So after hundreds of seconds, the survival fraction has gone down to 1 out of 10,000 or 1 out of 100,000 of these poor microorganisms in this experiment survived, but still not all of them were killed. However, this is on the assumption of a particular amount of ultraviolet light coming from the star. And this is something we've been assuming in all our work up to now, and in fact, the entire field has been assuming in all work up to now, that flares have a canonical temperature, and usually we assume 9,000 Kelvin, because that's what the few flares we've seen from other stars. We've seen more from the sun, but that's not the situation we're in. We're looking for flares from cool stars. That's what the few flares we've seen from cool stars up to now have looked like, 9,000 Kelvin. However, if you've got higher temperature flares, you can produce vastly more ultraviolet light. This is it's a black body spectrum sigma t to the 4 type thing, that if you see a certain amount of visible light coming from the flares, that has very different implications for the amount of ultraviolet light depending on how bright the star, depending on what the temperature of those flares actually was. And so this is something that Warder set out to answer. What temperatures do these flares actually have? And this is something that we can do with TESS, because TESS observes in the red, Evryscopes observes in the blue. And that means that despite TESS being in space and having much higher photometric precision than we have, we can find flares that Evryscope sees and TESS sees simultaneously from the same star, same flare, and get colors of the flares, and that allows us to constrain the black body temperatures of those flares. So that's what this looks like. This is Evryscope data versus TESS data. And basically you can see this immediately, this flare is brighter in Evryscope data than TESS data because the flare is blue. And the amount of blueness, you have to do a lot of work really figuring out the blackbody curves and so on, what you can really tell in terms of the where you are on the blackbody spectrum and so on. But it turns out we can constrain the temperatures of these flares quite well. So this is a measurement of the temperature of this particular flare as a function of time. We can even do this as a function of time. And this flare got up to 50,000 Kelvin. Our assumptions of 9,000 Kelvin for the big bright events turn out to be very wrong. We can do this for lots and lots of flares. And what Ward has shown is that temperatures, the typical temperatures of the flares increase strongly with energy. The big, bright, rare flares that you really need a survey like Evryscope to pick out, because you need to monitor lots of stars all of the time, tend to be the world-destroying ones, tend to be the ones which have much, much higher temperatures and therefore vastly more ultraviolets than we have been assuming, and the biologists have been assuming many orders of or at least one order of magnitude more ultraviolet than we were expecting. And so this is something we've only been able to do because we have TESS and Evryscope observing simultaneously. It also turns out that the biggest, brightest flares last longer with high UV emission. So not only do they have much more UV, but the UV lasts longer, and that is also a very bad thing for life. So with that in mind, we really want to get stuck into the effects of these flares on the planets. And we really want to go beyond what we can say from Evryscope and TESS, which is what does the black body spectrum of these flares look like, to really start to understand the astrophysics of the emission mechanisms from these flares, because it's not necessarily a good assumption that these are all black bodies all of the time. So what we need to do is to get spectra of these flares. And this is tough. This has typically been done by surveys that work on individual stars. You point a telescope at an individual star and you wait for it to flare. Now, a typical star, a typical M dwarf will produce a major superflare every few months. So that's a long time to wait, especially as you are, in the daytime, you're not sensitive to those flares. Across the sky, though, Evryscope sees about 1.5 extremely large flares per night. And we can actually, and dozens of smaller ones. So we can actually just sit there with Evryscope and using the fast transient system, just wait for something to happen. So this is Hank's fast transient system working here. This is a very crowded field. This is a very difficult one to do subtractions in, but the subtractions worked quite nicely. And you've got before image on the top, after image on the bottom, and then superflare, a superflare going off in that image. And as you can see, the superflare is big, bright, and obvious. And this gives us the opportunity to catch those superflares as they happen. And we're very lucky at UNC to have access to telescopes that can do this. So this is a zoomed out view of the Evryscope observatory site in Chile. In the very center of the image, you might see some blobs on top of a mountain there. That's the domes at the Evryscope observing site. The Evryscope is too small to see in this image. Right next to this, where this was taken from is the SOAR telescope, and that SOAR telescope is UNC's 4-meter class telescope that can do immediate follow-up of those flares. They're on almost the same mountain. And we've actually started to be able to do this. We can get to those flares within minutes of them going off. Our record at the moment is something like 10 minutes. We're trying, and the NSF has funded us to push that down to 2 minutes from the flare going off, which will allow us to measure the spectral evolution of these flares as they occur across a whole range, building a light of stars, building a library of superflares as they happen. This is an example. You can see this is a spectral sequence of those images. On the top, you can see the emission lines and then the continuum getting fainter and fainter. The bottom is a time-spaced survey of those spectra. You can see the emission lines starting at the bottom there, bright and fading as time goes on towards the top, starting bright and then fading out. And we'll be able to nail down the astrophysics. And because of SOAR's, quite frankly, world-beating ultraviolet sensitivity, we'll actually be able to get some constraints on the ultraviolet emission from the flares directly rather than assuming black bodies. And so that's what we're working on at the moment there. It's also worth saying that when a planet gets hit by one of these flare events, we would expect to see massive auroral emission from the planet. And think of what happens when you have high solar activity on the Earth. You get aurorae, which can be visible as far south as Chapel Hill, very occasionally. When one of these superflares hits a planet, or at least the proton ejection associated with superflare, you could imagine aurorae occurring everywhere across the planet, incredibly brightly, hundreds of times more brightly than we see with the Earth. And if you knew where to look, and we're monitoring all the stars all the time, so we do, if you knew where to look, you might just see a little speck of green light occurring next to a star as it goes off from that auroral emission line. This might actually be a way of not only detecting terrestrial planets, but directly measuring the amount of oxygen in their atmospheres from that auroral emission. That's speculative stuff, and the best we're likely to do is measure upper limits on all of those things, but those would still be pretty spectacular upper limits to get. So that's what we're working on there at the moment. So very briefly, I'm going to finish off by moving out of the galaxy to talk about something totally different, because as I said, I'm talking about a small fraction of the science that we can do with these systems. But I wanted to mention a totally different survey we're doing just for illustration, and that is a gravitational wave survey. You've probably read about, thanks Josh, I see 10 minutes to go, that's perfect. You've probably read about gravitational wave events occurring detected by the LIGO Observatory. Was a spectacular discovery a few years ago of merging black holes happening and actually seeing the gravitational wave emission from that, which allows us to confirm Einstein's theories along with a whole range of other physics. If instead of black holes colliding, you have neutron stars colliding, they arguably get even more interesting events, because there, instead of just really space-time colliding, with neutron stars there's stuff, and stuff does interesting things. So these events are called kilonovae, collisions of neutron stars, and they produce both gravitational waves and optical transients visible across the electromagnetic spectrum as these stars get very, very messed up as they collide. And these events, an individual one of these events allows us to get an independent measurement of the expansion rate of the universe, which is really something that's up for debate at the moment and a really important measurement to make. They're also the source of most of the heavy elements in the universe. Anyone who's got a gold ring on, for example, that was in the center of one of these explosions, most likely. At least a large fraction of the gold probably was in the center of one of these titanic explosions. Probably the other side of the galaxy when it happened. We can start to understand the central engines of these, the equations of state of the neutron stars in these really extreme environments, and so on and so forth. We want to find more of these events. These are the types of events that LIGO spent billions of dollars finding. The problem is, when LIGO produces an event trigger, it produces something like this, a banana on the sky. So this is a LIGO event trigger that says, we found a gravitational wave event coming from somewhere on the sky, and it's somewhere here. And the reason you see this banana plot is this is multiple detectors across the Earth triangulating the position of this event based on essentially the arrival time of the gravitational waves. Searching that large area of sky rapidly enough to take a spectrum of an event as it occurs is a real challenge with a conventional system, because you have to get a telescope and tile across all that large area of the sky as the event occurs. And you want to get these things really early on so you can see the early time evolution, the actual explosion as it happens. With Evryscope, we have a chance of seeing these. Actually, the first kilonova ever detected, we were so close. We have a field of view, which is the size of the human eye's field of view, and the event occurred 3 degrees outside our field of view. This is an image of the Evryscope image data that we took and the position of the first kilonova event. That would have been really cool. We would have been there so much earlier than anyone else, but it was just, you know, random luck that we weren't there. But this survey, but the thing is, we don't even know how bright an object like this would be early on. No one has gotten to these objects within even hours of the detection. And so we don't know if it's going to be extremely bright enough for the Evryscope to see, or bright or so faint that we couldn't see it. It's totally uncertain. And so this is, we just want to get there initially so we can even just see how many of these events are detectable. But we can actually go beyond that. So we've got a NSF-funded program in collaboration with the University of Florida and Monash University, which is called LiveOaks, the LIGO Virgo Evryscope Optically Assisted Coalescence Search. And the idea here is immediately on LIGO detecting something, we've actually got hooks into the LIGO databases, so that immediately as LIGO detects something before it's publicly released, we get a notification and we can go look in the Evryscope databases to see if we saw something simultaneously and target other telescopes at it immediately. But what's more than that is actually we're getting triggers for LIGO events which are not bright enough to reach statistical significance in their data sets. They're not sure about them. These are kind of 2 sigma, 3 sigma events rather than the 5 sigma ones that they will typically publish. However, if we can see those and we see a coincident optical transient, that vastly increases the chances that it's a real LIGO event. And our estimate is, and I'm going to see if I can duck down underneath that part of the slide, so I'm covering it there. LIGO plus Evryscope together gives about twice as many events as LIGO alone. When you think how many billions of dollars LIGO is spending to find individual events, if we can double that event rate with Evryscope, that's a pretty interesting capability. And so we've got a paper coming out on that soon, but the survey is actually already working. We've put out a release using some of the first results for a rapid follow-up from these LIGO events. Okay, in the last minute or minute and 30 seconds, I want to talk about the next generation system because, of course, Evryscope is being scientifically productive, and so we're thinking about the next thing we want to build. And we want to build a big Evryscope, one that's capable of going way outside the galaxy, not just for individual events like LIGO transients, but supernovae across every nearby galaxy, gamma ray bursts across the entire sky to the edges of the universe. And this is the system that we are planning to build. So we call this the Argus array, and think of it as an Evryscope scaled up by a factor of 10 in every direction, which means about a factor of 1,000 in total. So there are 1,000 individual telescopes in this Evryscope, in this Argus array, and these are large telescopes compared to the Evryscope camera lenses. I'll show you how large they are in a minute. They're kind of this size as opposed to this size that we had before. Together, we have about 650 telescopes covering the entire sky, much the same way as the Evryscope, except rather than a 6-foot dome, we've got a 30 to 40-foot dome. This is a major observing facility that will have a total of 40 gigapixels on the sky. And this is enabled by off-the-shelf technologies, off-the-shelf, really amateur observing telescopes that are getting really good. And so we can generate this telescope that has a 20-meter squares collecting area. That is one of the larger optical telescopes in the world. In fact, we're actually looking at a design at the moment that would make this the largest optical telescope in the world, just by putting together a lot of cheap off-the-shelf telescopes and really using them in the Evryscope way of looking at the entire sky all the time. We call it the Argus array because there's a Greek god who had many eyes. No, actually, I should be honest. We call it the Argus array because in Star Trek: The Next Generation, the Argus array is a Starfleet telescope that's multiplexed across the sky to look at images. We can't do faster than light observing yet, but we thought it was a cool name, and so we've stolen it. This is the performance we expect for the Argus array. So on the x-axis is the cadence, so in hours. And the y-axis is the depth in magnitude, so it's a logarithmic scale. In yellow and red, you see all the other sky surveys. And green is Argus in the 2-minute snapshots, 40 gigapixel snapshots we'll get across the sky, and then coadding to go much deeper. In fact, we'll be able to coadd over the course of a few days to go, for the astronomers in the audience, a magnitude deeper than any other sky survey like ZTF or anything like that. Actually 2 magnitudes deeper than ZTF. Almost as deep as LSST on it. It's now the Vera Rubin Observatory, almost as deep as that. And actually, the size of these points on this plot is the étendue, the light collecting power of the systems. And suffice to say, the Argus array has a 30% larger light collecting power than every time domain astronomy telescope ever built up to now put together. So it is a large system that will allow us to really cover the sky, go deep extragalactically, as well as going into our solar system looking for the faintest asteroids. We're going to have a fast observing mode that will have second cadence that will allow us hopefully to detect occultations from small objects in the Kuiper belt. We've got 20 separate science cases for the system. And this isn't vaporware, at least not yet. We've got a prototype system. This is one Argus telescope. The black holes in this circle here are individual Evryscope cameras, so you can see the size of an Argus telescope compared to an Evryscope camera. This is quite a scaling up. We're actually funded by NSF as part of the Mid-Scale Innovations Program for a prototype system, about $1 million prototype system to retire the risks for building the full array. And hopefully the prototype will be done in the next year or so, and then a year to 2 years, and we will be able to go on to building the full array, hopefully by 2025 or so. So I will finish there. Thanks very much for your attention.
Thank you, Professor Law, for a beautiful talk. I'm sure people have questions. If you'd like to use the raise hand feature, I will try to get you. Let me just start off by asking what I think is the obvious question. You see all these flashes all over the sky every night. What are they? What is generating, like what substance is reflecting the sunlight?
What's in Earth orbit? Yes, I was a little vague about that because it's something that we really need to nail down, because we need to nail down the distance to those flashes. So, and to the individual flashes to figure that out in detail. One of my students is actually doing that, fitting orbital tracks to the flashes. We've traced some of them to existing satellites, but very few of them. We think actually most of these are coming from debris. So paint, even things as small as a fleck of paint, which is shiny on one side, could produce these flashes if they're spinning rapidly enough. In fact, normal satellites won't produce the flashes because they're rotating too slowly to produce millisecond timescale flashes. You see them slowly moving across the sky and produce trails in astronomical images. These have to be spinning really fast, and the way you make something spinning really fast is you have collisions in orbit that lead to that debris, which means they're not going away soon. Their numbers are only going to increase.
I just realized I violated my own rule, which is to ask first for questions from students. So are there any students who would like to ask a question? Yeah, Nathaniel.
Can you hear me all right?
Yep.
Yes.
I really enjoyed the presentation. I just wanted to ask with the Argus array, what is the types of, is that a Celestron telescope? Like what are the models for or even with the current Evryscope array, what's the difference between like the telescope apparatus and like the lenses themselves?
Yeah, so good eye, that is a Celestron telescope. It's a RASA telescope. We're looking at different options. So we're not completely wedded to that telescope, particularly in its size, but we're also talking with other companies. We're getting into the details of that right now, but the Celestron RASAs look quite good for the prototype system. The Evryscope itself is, I said, camera lenses you can buy in Best Buy, and I literally mean that. We started out with $2,500 Canon camera lenses, which are the 85mm f1.2 lenses. We ended up actually evaluating the cheap Korean knockoff versions of those, the Rokinon 85mm f1.4 lenses, and they turned out to be slightly better than the Canon lenses, even though they're $250. And the reason for that is, I think basically they optimize to focus at infinity rather than focusing everywhere like the Canon ones can do, and so they do better for astronomical imaging. So it's amazing. For the Evryscope, the camera lenses are actually one of the smallest components of the budget for the system. We're actually, most of the budget for the system, we've spent about $2 million on the data analysis pipelines for the system, the $1.5 million for the data analysis pipelines and $500,000 for the actual hardware for the systems. The camera lenses are a tiny fraction of that. For the Argus array, it's a bit different actually. The telescopes become more of a fraction of the budget for the system because it's they're just much bigger and a lot more glass.
Bruno Sanchez.
Hi, excellent talk. It was super interesting. Regarding this Argus array, I'm going to ask more questions. Sure. You're showing magnitudes, depths, and my question is, because I don't imagine how these telescopes are working together. Are they imaging the same? And it says over there, like in a tiny word, reconfigurable array or something, or pointing.
Yeah.
Something like that. What does that mean? Is that the telescopes can point to the same area in the sky, or are they going? So that's, you're talking about the collecting area, but it's distributed among the sky, right?
Right. So it's solely the reconfigurable is solely for the prototype. Basically, we're going to have fewer telescopes than we have slots to put telescopes in, so that we can try out different organizations for the array. The full Argus array is tiling over the entire sky. So each of the fields overlaps with the next telescope along. And so what this means is it's like the Evryscope. Every part of the sky gets 6 to 8 hours of observing time from a 20-centimeter telescope every night. And what that means is, if you look at, for example, the survey lifetime of the Vera Rubin Observatory, in that time, each of our telescopes have about, I need to check the exact numbers, but I think it's 2,000 times less collecting area than the Vera Rubin Observatory, because the Vera Rubin Observatory has this equivalent of a 6-meter class telescope mirror. So 2,000 times less glass, but they observe each part of the sky for 5,000 times longer over the course of the survey lifetime. And that's how we can go deep, because we have vastly longer observing cadences. So the VRO looks at each part of the sky for 30 seconds every 5 nights or so, depending on which survey you're doing. The Argus array looks at each part of the sky for 6 to 8 hours each night and gets those deep integrations. So we get the fast cadence and we get the deep integrations simultaneously from that setup.
Thank you. Thank you.
Let's open it up to everybody for further questions. Chris, Walter?
Hi, nice talk. I was curious, first of all, do you always observe in the same bandpass? And then I was wondering, could you say something about the imaging array? How are you focusing this all down onto a plane of CCDs? How does it work?
So do you mean specifically for Argus or for Evryscope?
For both, actually.
So they actually work very much in the same way. So I'm not going to go back through 100 slides, but I'll leave the Argus display up. So first of all, the filters. For Evryscope, both Evryscopes at the moment work in the blue. So G-band, Sloan G-band specifically. We actually have red Sloan R-band filters in the northern Evryscope because we have more red sensitive CCDs there. We're not running that survey at the moment because we wanted to build up cadence in the blue. And also while TESS was observing in the north, we wanted to be observing simultaneously with TESS in a different passband. For Argus, I mean, it's literally, in terms of what you're asking about the imaging plane, it's one CCD behind each telescope. And so think of it as separate telescopes. They just happen to, when put together into this array, cover the entire sky. And so what's going on is these are individual telescopes. And the idea is to do this very simply. So with off-the-shelf components. So we're not trying to build arrays of CCDs or anything like that. And by doing that, we can reduce the costs of the individual telescopes by 1 to 2 orders of magnitude compared to building them in a custom sense. And so that's how the total budget for the Argus array is about $12 million, including the scientists and the pipeline development, because we're leveraging a lot of Evryscope pipeline development. The actual hardware budget is, depending on what design we choose in the end, somewhere between $5 and $10 million. And we can do that simply because we're buying the off-the-shelf things and not trying to do anything fancy, not trying to do anything really new, to be honest, just putting it all together in a new way. And so we're spending thousands per telescope rather than millions. And it gives us this equivalent of a 5-meter telescope in terms of collecting area for, as I say, $5 to $10 million of hardware costs. That's almost the collecting area of VRO, and VRO is $1 billion project. So we've really been able to leverage the off-the-shelf things to really reduce the cost, which is important because it means we're much more likely to be allowed to build it. So,
thanks.
Joaquin? Drew?
Sure. Something that might be a little obvious, but maybe not so much for someone that hasn't done a lot of data analysis, especially not on this scale, right? So you're generating a ton of data, and you're not going to get that data, I guess, through the internet to your office, right? So all that analysis, and I think this was written here on the bottom right of the slide, has to happen there, right? Remotely. Is that right? It's a huge amount of data.
Exactly. For the Evryscope, we just, we have hundreds of terabytes of Evryscope data. Frankly, 10 years ago, that would have been prohibitive for doing a project at all. But nowadays, you can get 100 terabyte storage in a thing the size of a shoebox for 5K. So it's feasible with Evryscope. With Argus, a 40 gigabyte, actually an 80 gigabyte image every 2 minutes. That's a challenge.
Right,
and so what we're actually doing is we're kind of doing an analogy to the particle physics approach. So a hierarchical data processing system where we process the data as it comes in real time and throw out parts that we're not interested in, coadd the images as they come in. So we're averaging together over timescales on the image while doing real-time detection of new events at the full high-speed cadence of the system. And I mean, the proposal for the Argus array prototype was a 30-page proposal, of which I think 5 pages was building the hardware, and most of the rest was doing how we do the science, how we do the data analysis from the system. Because it's going to be a challenge, but I think we've figured out how to basically reduce the data rates in this hierarchical approach to the level that we can do it.
That's very cool. Otherwise, you would need someone to fly over there, and we getting the data, right, and flying it back would be easier than getting it through the web, right?
Yeah, yes. I mean, even with the biggest pipes we have nowadays, we couldn't do that for Argus. Evryscope, we can just about do it from our Californian site. And if we can get it onto the Google Cloud and so on, there's actually quite a lot of fun things you can do with very fast processing. But maybe like Evryscope, things get easier 5 years after we build Argus as people become more. 100 gigabit connection doesn't become totally impossible and that kind of thing.
So a related question is, maybe you said it already, this telescope, the Argus, is going to go to Chile. Is that the plan?
Actually, it's going to be a Northern Hemisphere telescope. Oh. And the reason for that is it's a wonderful complement for LSST, the Vera Rubin Observatory, which is in the south. And there's not any point in observing exactly the same sky area VRO is going to observe at similar depths. So by going into the north, we get the whole other side of the sky, and also a lot more follow-up resources, a lot easier follow-up resources from the Northern Hemisphere telescopes. Plus, it'll be easier to have it in North America, to be honest.
I imagine it's easier to troubleshoot anything that could happen with this big system, right?
Yeah, when you've got something this large with 1,000 telescopes in it, reliability is even more of a thing than it is with the Evryscopes, and so yeah, we're thinking North America would just make it more feasible.
Let me get Elise Lebulico.
Yes, I just had a question about the genesis of life due to UV radiation. You showed that plot where the flares could not account for enough radiation to make life. But what about just the radiation not due to the flares, just like the continuous radiation? Is that taken into account there, or is that?
Yes, that is taken into account. In fact, these stars are so small and cool that they have virtually no quiescent ultraviolet radiation. Basically, the black body spectrum from them at a 3000 Kelvin black body just doesn't really go out into the ultraviolet at any reasonable level. There are much smaller flares that happen all of the time, but they're orders of magnitude below the UV impacts of the large flares. They are included they would be included way to the left of this graph, way outside the zones to produce enough ultraviolet to either affect the planetary atmospheres or affect the formation of life. I did have a slide on that. I'm hoping it might be in my backup slides. I'm looking at the moment. No, I don't think it is. Ward will be annoyed at me that I don't have that slide to hand. Ward has a beautiful slide about exactly this, but yeah, these cool stars don't produce much ultraviolet. What we always do is we actually compare this to the early Earth. And in the early Earth, we've got the sun that is not only producing a large amount of ultraviolet just from being a hot star, which produces a large amount of ultraviolet, but also from flares. And generally, the flare environments that we see from these big flares actually produce more ultraviolet, significantly more ultraviolet than the early Earth sees.
Okay, thank you.
I don't see any more hands up right now, so let's formally close the colloquium. Thanks very much, Nick, for a beautiful talk. And so people should feel free to check out now, but maybe you can hang on for a few minutes if there's some people who would like to stick around to chat. I wish we could offer you some cookies, but that's
I'll go find some
for another year, I suppose. Thanks, everybody. So Nick, I did want to ask you one thing just about